Hello everyone, welcome back to my channel, Predicting the Future. Today we're gonna look at some of the properties of conditional expectation. Those properties that we usually see in the regular expectations. Uh, this, all applies in conditional expectation. And we're also gonna see some properties that we don't see in the regular expectation. Uh, and those properties are very beautiful. So first, let's look at some of the basic properties. So those properties are listed here without proof because the proof are very easy. All you have to do is to apply the definitions of conditional expectation that we mentioned earlier, and then just expand it out. You usually will be much easier to figure out. Very similar to what we see in regular expectations. Some may not be that obvious, but if you look at, for example, the Jenson inequality, you probably will gonna look at how we prove the Jenson inequality in regular expected value functions, and then apply the same principle to the conditional expectations, and it won't be hard to figure out those proofs. So let's look at some of the properties. Linearity, linearity is just because of this. Is expected value is integral. Integration is a linear operator. Monotonicity is basically because if x is less than or equal to y, almost surely you get the same for conditional expectation. Chebyshev inequality, it also applies for conditional expectations that we see in the regular Chebyshev inequalities. Markov inequality is just a special case of Chebyshev inequality, but we use that more often. And then monotone convergence, that's basically from the fact from the measure theory, where if I have xn converge up to x, both are positive, and x is integrable, then so then this one will converge to expected value of x given f. So I'm missing some here. And then Jenson inequality here is the same as what we see for the regular condition, regular expectations. Cauchy-Schwarz inequality is just the fact of a Hilbert space, an inner product space, and expected value of this is something we also talk about in the probability essential videos, where you take the expected value of x of given some sigma field f, you get expected value of x, and that is just using the definition of conditional expectation by integrating over the whole space at omega, and that's basically from the definition. Filtration, if we have two sigma fields, f1 is including f2, then if we take the expected value, the representation of the expected value of given f2 on expected value of x given f1 will always be choosing the smaller sigma for f1. So that will be expected value of x given f1. And same if we switch to f1 and f2, we still the representation of the conditional expectation is still choosing the smaller sigma field. The proofs are also pretty straightforward just from using the definition of conditional expectation. So the next one is this one will be very interesting. It will be very, very useful whenever we want to prove something. This is a very, very useful theorem. So what it states is that if x is f measurable and y is integrable, as well as xy is also x times y absolute value is integrable, then the expected value of xy, expected value of xy given f is just x times expected value of y given f. So we can move the x also out of this conditional expectation when x is f measurable. Before we prove that, let's see intuitively, right? So we want to find some expected value average of some x times y, given given this because x is f measurable, which means that if we know f, we know x. So if we already know x, then our best guess is just x times the expected of y given f, right? So that's very intuitively makes sense. The proof is pretty much 3 steps. We prove it first. We assume that x is an indicator function, and that's we want to prove that this is true when x is indicator function, and then we're gonna and because of that we can apply x to be where x is just simple functions. So it's a sum of indicator functions times some constant. So that's simple functions. Because that applies, then because indicator functions is correct, the simple function works as well. And then we can further to prove our any function x. All we have to do is to separate into 2 steps. First, we can assume that x is positive, and then we can use the monotone convergence theorem by approaching x by a positive simple function, increasing positive simple function xn, where xn converge up to x. Then we can use the monotone convergence theorem to check that this is also true for positive x. And the last thing to do is to separate x to be x positive and x negative, and that will apply eventually for any x. So what we left is all we have to do is check for indicator function when x is indicator function. So when x is indicator function, then we just have to check that this is true for every e in f. So this is what we have, and that's by definition of conditional expectation. It's just an integral of indicator function 1a times y. And because it is indicator, so we can just write it as e-intercept with a, and then this is and by definition, this conditional expectation. This will just be expected of y given f, and then we can move back the a into the integral, so that becomes this, and that's exactly what we want to prove. So that proves this theorem, and so that just so that's prove our theorem. And the next one is also very important. I mentioned that very early when we talk about conditional expectation. I mentioned that the version of the conditional expectation is a projection onto a functional space of f measurable. So if we have so that's something we're gonna also see here. So suppose so let's first look at like functional space, Hilbert space here. So if so suppose x belongs to the L2 space, where the functions in L2 are f0 measurable. So the definition of L2 f0 is just the function y, the measurable function y, or random variable y, that the inner product is finite. And also let's suppose that there's another measurable space f, where the L2 space of f is a subspace of L2's f0. So that is that if we know something, but we don't know the whole space, right? So by giving those assumptions and definitions, then what this theorem says that the version of y, where y is f measurable, the version of y that minimizes the mean square error, so this is what we see in mean square error, is the conditional expectation of x given f. So when we replace y with the conditional expectation x given y, this is minimized. So let's prove that. And that makes sense, right? So this is a projection. The close y to x is the projection of x on the space of where y lies in, right? So let's prove that. So suppose y is L2 measurable in the L2 space. Then let z to be the expected value of x given y, which is L2 measurable too, is in the same space, minus y. So z is also in L2f. And then let's expand that. Let's expand this mean square error. When we expand it, we replace y to be expected value of x given y plus that. So that was y being replaced. And then we expand this square by the linearity of an integral. We get three terms. The first term, which is a positive term. The second term is 2 times a times b. And then the last term is square of the last term. So what we see is that, in fact, remember we talk about this is actually this expected value z times the x minus expected value ex given f is actually 0. Why? Let's prove that. But before we prove that, let's visualize what this means. So what is x minus ex given y, which is, ex given f is a projection of x. So x minus its projection is some function that is orthogonal to the functional space of L2f, right? And z is on the L2f. So what this is doing is an inner product of a function that's orthogonal to the space, and that should be 0, right? And that's exactly what it is. So if we expand it, we get expected value of z times x minus expected value of x given f, and this is just exactly expected value of x z y, and that's just 0, right? So the middle term is 0. To minimize the mean square error is to minimize z, and z is minimized when z is 0, which means that mean square error is minimized when y is equal to the conditional the expected value of x given f, and that proves what we have been used all the ways in regressions. What we're trying to minimize the mean square errors, and it's just the same thing here. And that's it, everyone. Hope you like it. Bye.